Hey everybody, it's Miss Rector here again. We are going to go over Chapter 4, Section 1. So, basically talking about light today. So, in the very first part of your book, you saw a picture like this one here on the left. And you might think, well, why is this picture even here? So, if you look at this picture, on the left, let's start with the one on this side. What do you see? Well, some people see an old woman, some people see a young woman. When I was taking psychology classes, they would say, older people tend to see the old woman, young people tend to see the young woman. So you guys can probably see the young woman. She looks like she's looking away. She's looking in that direction over there. That would be her eyelash and her nose and her chin. That's her neck as she's looking away over there. She's wearing some big hat with a big plume kind of thing, feather on it. If you see the old woman, you have to just look at it in a different angle. This old woman is not looking away from you. She's looking sort of down into this corner. So this is an eye, and this is another eye. She's got this big nose. And then there's her mouth and her chin. And she's also got more of instead of a stylish hat, she's got sort of a shawl over her hair here. In this picture, you might see a face, or you might see the silhouette of somebody playing the saxophone, right? So, why are we doing this in chemistry? Well, turns out light has this strange duality as well. It travels through the vacuum of space, like it doesn't need a medium to travel through. It doesn't have any mass like a particle does, but it behaves like a wave and like a particle. So, we'll talk more about that in the upcoming sections too. So, electromagnetic radiation, it travels as a wave, but it also acts like this little stream of what we're going to call photons, like little packets of energy acting like particles. So, let's get to talking about the parts of the wave today. So, if you were with me in the class, we talked about this already, but never hurts to repeat, right? So first of all, let's look about the parts of a wave. This is a wavelength. So the distance from one crest to the next is a wavelength. This little symbol, it's called a lambda, it's Greek letter, and it is the symbol for a wavelength. So wavelengths we'll usually talk about are pretty small in the nanometer category. So this is going to bring up a lot of that math we learned at the start of the year. So if you've got a scientific calculator handy, you're going to need that in a few minutes, and you're also going to need to remember how to convert from nanometers to meters. Oh my goodness, significant figures too. What the heck? So, on that slide, subatomic particles behave like particles, but also behave like waves. So, that's where things get a little weird because the way Newton described things with his laws of physics doesn't work with subatomic particles. And the laws that work with subatomic particles don't work with Newton's laws, like when you're talking about planets and things. So there can't be two separate laws of physics. There can't be separate laws for big things and little things, right? There has to be one set of laws. So that's where quantum mechanics comes in, and that's where people don't necessarily feel comfortable with it because you have to think of things a little bit differently than just your everyday observations. All right, let's talk about parts of a wave here. We've got wavelength. So the wavelength could be the distance from one crest to another crest or one trough to another trough. Basically, it's the whole length of the entire wave to go through a whole wave. What's that distance, right? Then we talked about the amplitude. So it would be the height off of the origin. So the distance from the origin here to the crest or the origin to the trough. And we mentioned in the classroom part that the amplitude is responsible for like the brightness of the light, where the wavelength is responsible for the color of the light. If this was a sound wave, The amplitude would be responsible for the volume, where the wavelength would be like the pitch, so a high or low frequency, high or low pitch. So brightness of the light depends on the amplitude. Where the wave crosses the origin, by the way, that point is called a node. I don't think we brought that up in class the other day. All right, so waves have a frequency. What is a frequency? We're going to represent it with this Greek letter. Kind of looks like a V. This really isn't the best. It's sort of a curvier V than that, but limited by my characters on the keyboard here. It's a Greek letter called a nu, and we use that for frequency. It means cycles per second. So you talk about the speed of light. The speed of light is the same regardless of the light, right? It's constant. But the frequency, how many cycles the light goes through per second, that can change due to the wavelength. So here is the formula for calculating this. You have lambda, the wavelength, times the frequency, so how long is the wave, times how many cycles per second there are, and that should equal the speed of light, which is c. So c is a constant, stands for the speed of light. You just need to write this number down and memorize it here if you need to. 3.00 times 10 to the 8th meters per second. That's how fast light travels in a vacuum. So if you go ahead and write this formula down, because you're going to need that for one of the activities you do after this. All right, let's take a look at calculating some of these problems. Here's where all that stuff comes back from the beginning of the school year. So we've got wavelength times frequency equals the speed of light. Remember, speed of light, always the same. So this is like a plug and chug algebra problem. I always know what this is going to be. So if I know one of these, I can calculate the other one. If I know this, I can calculate this. If I know this one, I can calculate this. And a little algebra will tell you, basically whatever you're calculating, you're going to take the speed of light and divide it by the one that you're given to get the other. So we're going to use this formula, but because the speed of light is given to us in meters per second, we're going to have to make sure the wavelength that we calculate is also in meters. All right, so if it's given to us, like it will be here in nanometers, we're first going to have to turn that into meters so that we can use this constant. Otherwise, I'd have to have this in nanometers per second, which would probably be trickier to calculate. So 1 nanometer is equal to 1 times 10 to the negative 9th meters. So we'll have the little stair-step chart here in a minute. So we're going to try these problems, or at least I'm going to do one of them with you. You'll do the other one by yourself here in a second. So if you need to pause this, get yourself a piece of paper, get yourself a calculator. Scientific calculator would be fantastic. And then come back and we'll join it together, do these problems. I am just going to go on and hit escape and pull up a Jamboard. So we're going to work on this first problem together. The wavelength of light is 800 nanometers. What is its frequency? So let me go up here to our little Jamboard here. Oh, it's too far ahead. Okay, so we have, this is our formula. Again, excuse my terrible handwriting on these things. There's wavelength, which we know is the wavelength, but we need to get it in meters. The frequency, which is always going to be in like s to the negative 1, so that's like per second. So how many cycles per second is it? And then, of course, the speed of light, c, 3.00 times 10 to the 8th meters per second. So we plug in what we know. So what do I know? I know this is 800 nanometers. I don't know what nu is. I don't know the frequency. That's what I'm looking for. And then I know the speed of light, 3.00 times 10 to the 8th meters per second. So to get this calculated, remember, this is in meters. I have to get this in meters before I can do any math. So to do that, you can remember our stair-step chart if you want. So we went down here, there was milli, then this down here to all the way to nano. So we're at nano and we're going back up 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. And so we're going to move the decimal 9 places to the left, which is where we got this number. Moved it over 1, 2, 3, and then 4, 5, 6, 7, 8, 9. Of course, you could turn this number into scientific notation and just say 8 times 10 to the negative 7th, right? 1, 2, 3, 4, 5, 6, 7. Sorry. So once you've got that in meters, then it's just some simple calculations after that. You're going to take your speed of light divided by your wavelength, and you come up with the frequency. So 3.75 times 10 to the 14th, that's how many cycles it goes through per second. So that's the frequency of that wavelength. Now, I'd like you to take a second and try the other problem. In this one, you're given the frequency, so that'll go in for this. Of course, you know the speed of light, so calculate the wavelength. Pause it, take a second, and I will see if you're right. All right, I just did it on my calculator. I took 3.00 times 10 to the 8th, divided it by 93.1 times 10 to the 6th, and I got 3.22. There you go. No times 10 to the anything on that. But what would the units be? In this case, I would have to say meters, okay, because my speed of light was in meters per second. If somebody wanted to know it in nanometers, I would have to then use my chart and translate that out too. So you should be able to give them one of these, calculate the other one. All right. Let's talk about light and the spectrum. So here is the visible spectrum of light. This is what your eyes can see. As human beings, this is what our eyeballs are tuned in to see. We see red, orange, yellow, green, blue, purple. And the different colors you see are due to the different wavelengths of the light. So if you have a shorter wavelength, you're up here on the scale. Notice this is like 400 nanometers. Where down here, the wavelengths are more like 700 nanometers. So these are longer wavelengths down here, shorter wavelengths up here. That means there's going to be increased frequency, because if you have a shorter wavelength, then you can have more cycles per second. So that would be a higher frequency wave. So you see a different color. Now, we only see the visible spectrum, us, human beings, but other animals can see outside that, and some will see ultraviolet spectrum of light, some will see the infrared spectrum of light. We talked about that in class with the bees and the pit vipers. But for us, all we see with our eyes is the standard Roy G. Biv. Now, when it comes to this light spectrum, you need to be able to not necessarily tell me the exact number for each wavelength, but you should be able to tell me what's longer or shorter wavelength and what has higher energy or less energy. So the shorter the wavelength something has, the higher the energy it has. So when we light our Bunsen burners and we go for those orange-red flames, that's just so we can see it better. When we really want the hot flame, we adjust that Bunsen burner to the blue flame, the almost invisible flame, right? That's because those are shorter, higher energy wavelengths of light that will, sorry about that, that will mean more energy for our reaction to absorb higher temperatures and a faster reaction, hopefully. So that goes to this end of the spectrum. So as we move to this end of the spectrum, when you think of high frequency things, high energy things, you should think, okay, red, orange, yellow, green, blue, indigo, violet, and then there's ultraviolet, right? That's the UV light from the sun, gives you skin cancer, right? X-rays are beyond that. You really can't see those. They go right through your skin, though, so that your doctor can see if you have a broken bone. And then we talked about gamma rays coming off of those nuclear decay reactions. Again, going right through your body, right? So very high frequency, damaging your cells as they go through. On the other end, as the waves get longer, they're lower energy. You think, oh, less danger, right? Infrared, this is like the heat coming off of stuff. Then you've got microwave radiation. You're probably familiar with your microwave. And, then your FM radio, AM radio, those waves are bouncing through your house right now. If you turn it on the radio station, they would pick it up at that frequency that that station has, and you could hear. Then there's really long radio waves. Think like those ham radios that can travel, halfway around the world. So if you watch Stranger Things, those radios that that kid uses in there. So if I asked you a question like, what has a shorter wavelength, red or blue, you should be able to say, okay, blue is on the shorter, higher frequency, shorter wavelength, higher frequency, higher energy end compared to red. Okay. Or if I said, what has a longer wavelength, infrared or UV, you should be able to, in your head, say, okay, infrared's on this side, that's the red, those are the longer wavelengths. So I'm not asking you to memorize, the numbers like these, but you should know the general order of things on here and what has longer wavelengths and what has higher frequency with short wavelengths. All right, I'm going to let you stop there for today, and then when we come back tomorrow, we'll talk about how this relates to the atom. And in the meantime, you have a Google form to go and practice some of what you just learned. Good luck. Bye.